All right, good afternoon, class. This is what lesson is this? This is lesson 8 today. So we finished all of chapter 1. We're now moving into chapter 2. So this is section 2.2, lesson 8. And mostly what we're going to be concerned with today is finally starting to dissect what are different things I can do with a matrix, right? We've talked about how two column vectors can be added together, assuming they come from the same space, right? If you have a column vector, which is 1, 2, 3, and another vector 1, 0, 1, we know we can just add these together by adding their entries together, right? And so we're going to get something like this for the new column vector. We know that we can take a vector and we can multiply it by a scalar, right? If I have C times a column vector, well, then each entry gets multiplied by C, right? So we've seen this before. This step here is not new. We've done this before. What is new is that now I want to think about, okay, what about with matrices? Can I add matrices together? Can I scale matrices? Or what about multiplying matrices? We've seen that we can't multiply vectors, but we can multiply a matrix times a vector, right? Take our example we keep coming back to, A times X, right? So we know we can do a matrix times a vector. What about a matrix times a matrix? These are all things we want to talk about today in section 2.1. So first, what's going to be helpful here is to talk about some notation. I'm going to be talking about matrices. Matrix A, the A sub ij entry. So this is lowercase a with two subscripts, ij. The A sub ij entry is the entry of the matrix A in the ith row and jth column. This notation is going to be more important later in chapter 2. Not super necessary for today's stuff, but I want to go to introduce it here so we can get used to it because we are going to need it in the rest of chapter 2. So in practice, how does this work? Well, remember for matrices, when we're talking about the dimensions of a matrix, we always say rows by columns. Rows first, then columns. It's the same idea here. If I want to talk about something in the first row, second column, so we can write that here. The entry in the first row, second column is A sub 1, 2, right? First row, second column. So in practice, for example, if A is, let's say A is a 2 by 3, then it has 2 rows and 3 columns. A13, this makes up the first row. A22, A23, right? So this subscript here is really just giving me indices to tell me which point in the matrix am I looking at, right? Again, this notation is going to be more relevant for later in chapter 2, not as helpful for today, but that's okay. All right, great. So what are other things we can do with matrices? What's some other notation, other definitions? Well, we also have a notion of what it means to be a diagonal matrix. Now, diagonal matrices, they're first introduced here in chapter 2. But to be perfectly honest, we're really not going to come back to diagonal matrices until and maybe honestly like in late chapter 5, chapter 6, before we come back to diagonal matrices. Part of the point is that diagonal matrices and the process of diagonalization is going to be a super big deal towards the very end of this class. It's going to be one of the last topics we really talk about and dissect. Before we get to those chapters, we want to first get used to what is a diagonal matrix. Then when we get there later, we're already going to know at least a little bit of what's going on. So what is a diagonal matrix? Well, a diagonal matrix, or rather, a matrix is a diagonal matrix if, first of all, it has to be square if, one, the matrix is square, the square, right? 2, the only non-zero entries are on the diagonal, right? This is where we get the name for diagonal matrix then. In other words, it's 0 everywhere else. The non-diagonal entries must be 0. So the only non-zero entries are on the diagonal. What does this look like? Well, we've already seen the identity matrix. This is an example of a diagonal matrix. It has zeros everywhere that is not the diagonal, and the only place you find non-zero entries are on the diagonal. Now, of course, this doesn't say you have to have non-zero entries on the diagonal. It just says that's the only place for them to exist. So something like A equals 1, 0, 0, 0, 0, 0, 0, 0, 1. This is also a diagonal matrix. So there's nothing about being a diagonal matrix that says you can't have zeros on the diagonal, right? It's okay to have a 0 on the diagonal, and this is still a diagonal matrix. The only requirement is that everywhere besides the diagonal is 0. What happens on the diagonal? Well, who knows? It could be anything non-zero, or it could be 0. The only requirement is that the only place where non-zero entries are on the diagonal. Or to word it another way, if you look at the lecture notes in Canvas on 2.1, you could also say the non-diagonal entries are 0. That's the only requirement. The non on this left or right diagonal must be 0, right? That's the only requirement. Okay, why do we care about diagonal matrices? Well, on one hand, we like them because this identity matrix is really easy to work with and multiply, right? We've seen the identity matrix times a vector is just a vector. So part of the reasoning for why we care about diagonal matrices is that they're easy to work with when it comes to matrix arithmetic. More on that we'll talk about when we get into chapter 5, chapter 6, but I want to go ahead and whet your appetite for this definition here. Okay, great. Yeah, I did see with the last video, with yesterday's video, for some reason, it had like that glitchy thing happening with the video. I don't know if there was some kind of short in the cable for my camera I'm using, the webcam. I'm trying it in a different USB port. We're going to see if that makes any difference. I don't know. It hasn't done that before, except for some of these videos I've been making this summer. So hopefully this video is going to stay nice. So far, it looks nice, but we'll see. Okay, let's keep moving forward. So we've talked about diagonal matrices. Now let's actually start to break down how does matrix arithmetic work. Well, when it comes to addition and scalars, it's going to work the exact same way it did for vectors. So good news is that some of this is not going to be very new looking. So matrix arithmetic So we're going to say, assume A and B. So these are capital letters. In general, in this class, when I use capital letters are always going to refer to X is going to be a vector. And then other lowercase letters like the letter C is going to be a constant just because, well, the word constant starts with C, right? So capital letters, these are matrices. Let's assume they are both, assume A and B are both N, or let me use the same notation they're using here, M by N matrices. They're both M by N matrices. Then A plus B is simply so notice these are the same size matrices. So because they have the same size, they have the same entries, right? For each part of the matrix, they have a corresponding entry. So how do you add them together? This is just the result of adding corresponding entries together, right? So if I have a matrix 1, 1, 1, 1, and another matrix 1, 2, 3, 4, I'm going to get the answer just by adding the corresponding entries together. So the first row, first column, 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5, right? The exact same way we did for vectors. Now, we also, like vectors, have the requirement that in order to add two matrices together, they have the same number of rows and columns. If 1, 1, 1, 1, 1, 1, I can't add these matrices together. This doesn't equal anything. I can't compute it because there's no corresponding entries for me to compare to with this row 3. There's no row 3 here to use. So matrices, in order to add them, they have to be the same size. They have to be both a 2 by 2 or 3 by 3. They don't have to be square necessarily. They're just square in this example. But they both have to be the same. They both have to be M by N. So they don't necessarily have to be square. Only diagonal matrices have to be square. Okay, great. What about scalar multiplication? Well, again, it's going to be the same story as what we had with vectors. So let C be a constant. Then C times A is the result. It's the result of multiplying each entry by C. Exactly what we did with vectors, right? So if I have, for example, 2 times 1, 2, 0, 4, well, then my result is going to be 2, 4, 0, 8, right? Again, the exact same situation we had with vectors. So this is how we can add matrices together. This is how we can multiply a matrix by a scalar. We also still have all of this handy dandy distribution rules still apply. What am I talking about? Well, that just means that if you have, let's say, two matrices being added together in parentheses, and they're being multiplied by a scalar on the outside, well, then I can actually just distribute the scalar. This is CA plus CB. Or similarly, if, say, I have two scalars, C1, C2, these are constant real numbers being multiplied by a matrix, I can distribute the matrix across these constants, and it'll be C1A plus C2A. So some of these things are not going to change. They're going to work exactly the same way that you would expect them to from what we have with regular algebra. The trickiness comes into play when we start talking about how to multiply matrices. That's where we have to be careful. And so I want to highlight that next. But as far as like the arithmetic of adding matrices together, multiplying by the scalars, it all works the same way as what you would kind of expect intuitively. All right. So where does the messiness appear? Let's talk about multiplication. So first, when we're trying to multiply two things, so now I'm dealing with two different matrices, right? A times B. We already know that in order to multiply a matrix times a vector, however many columns N has, or sorry, however many columns the matrix A has, that had to match the number of rows for the vector X. Well, that's still going to be true. These two numbers must match before I can multiply matrices. If they don't match, then their multiplication does not exist. You cannot calculate it, right? So let's just suppose, okay, A has M rows. It can have any number of rows here. And let's say B has P columns. Again, I don't really care. Let M and P be some positive integers, right? The only requirement so far in order to multiply them is that these two numbers right here have to match. And actually, let me silence my phone. I don't know why it's going off so much right now. Okay, so these two numbers have to match here. Great. How do we do multiplication? Well, we know that A is just some matrix that has n columns, right? I have a A1, A2, AN, right? It has n columns. And B is some other matrix that has P columns, right? There's a B1, B2, B sub P. It has P columns, right? Okay, so far, nothing spooky here. This we already knew, nothing new. So how are we actually going to multiply them? Well, let's just break it apart one step at a time. A times B, this is the same thing as A times this matrix B with all of these columns, right? Well, I could think of this as a distributive thing of a linear combination where I can just distribute A and I want to multiply A times the first column of B1 times the second column of B2 or of B times the third column, right? if I kind of like distribute this matrix A, then my new matrix will be A times B1, A times B2, dot, 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 A times BP. Now I'm writing it out this way just to kind of give an explanation for how we can get our answer. Honestly, this is the long way to do matrix multiplication. In practice, as we continue in the class, you're not really going to be doing this methodology again. However, there are some instances, some applications where thinking of matrix multiplication in this manner can be helpful. All right, so let's see an example. How does this actually play out? Let's look at an example. So let's say A is the matrix 2, 3, 1, -5. This is a 2 by 2, right? And let's say B is the matrix 4, 3, 6, 1, -2, 3. So B is a 2 by 3, and lo and behold, these two numbers match. So great, I know I can multiply them. If they did not match, then the problem would stop here, and I would say, oh, can't do it, end of story. But here we can. Okay, so we continue, and we can use this formula we have so far. A times B is going to be the matrix A times B1, the matrix A times B2, the matrix A of this multiplication. B1, what is B1? It's the vector 4, 1. A is 2, 3, 1, -5 times 4, 1. Now, this is a matrix times a vector. We kind of like rewriting it this way because at this point in the class, we already know how to multiply a matrix with a vector. This is the same thing as a linear combination. So I have 4 times the first column. That's 8, 4, plus 1 times the second column. And we get a brand new column of 11, -1. Right? And so this will be the first column of A times B. This is 11, -1. All right, great. And so you continue the process. Now, for the sake of time and space, I'm not going to write it all out here, but basically it's the same thing. If you do A times the second column, well, you're going to get 0, 13. And if you do A times the third column, we're going to get 21, -9. 0, 13, 21, -9. And so, lo and behold, we have our answer. Now, a couple comments. One, try and do the matrix multiplication with this method, with this methodology, is multiply it times the first column. Take matrix A, multiply it times the second column. Take matrix A, multiply it times the third column. If this had been a bigger matrix, if A had been like a 3 by 3, or if A had been, or if B had been like a 2 by 5, I would have had 2 more columns I would have had to multiply before I would have gotten my answer, right? So first of all, this method is very tedious, and depending on your example, could take a while, and that wouldn't be so great, right? We don't like that. So that's the first point I want to highlight here. Second point I want to highlight here is look at the dimensions of the result, right? What happens here? This is a 2 by 3 matrix. Why did it turn out to be a 2 by 3? Well, however many columns B had, right? B1, B2 through BP, I had to multiply A that many times. I had to multiply A times each column of B. So the number of columns, let me do this in a different marker, so hopefully you can see what I'm trying to highlight here. The number of columns of B is going to tell you the number of columns of your answer. But how many rows do I have? Well, the matrix A is a 2 by 2. When I do a matrix, which is a 2 by 2 times a column vector, remember when we do linear combinations, the output of a matrix times a vector is going to be, it's a combination of the columns, right? If it's a combination of the columns, the output is going to be a new vector which has the same number of entries. How many entries? It's how many rows matrix A has. So you can look at the number of rows of A and the number of columns of B, the two outside numbers, to tell you what size your output should be. When you multiply the two matrices, what kind of matrix are you looking for? Is it a 2 by 2, 3 by 2, 4 by 5? Looking at these two outside numbers will tell you the dimensions of your, or the dimensions of the resulting matrix after the multiplication. Okay, so this is matrix multiplication using this kind of linear combinations methodology, this linear combinations argument. This is the long way and honestly the hard way to do matrix multiplication. Now let me show you the quick and easy way. How else could we do this? Well, remember when we've been talking about the dot product. What did the dot product say? Well, the dot product said that when you're trying to multiply two matrices, the result, so if the result is, let's say A times B equals a new matrix capital D, then this is the dot product here, dot product. What did the dot product say? The D sub ij entry. So this is the entry of the output, the entry of the matrix D, which is in the ith row, jth column, is the ith row of A, the left matrix, times the jth column of B, the right matrix. So in other words, if I'm trying to calculate this first entry right here, this is in the first row, first column, I want to multiply the first row with the first column. Well, okay, when I have a column, or when I have a row times a column, we know that's a linear combination. And so this will result in 2 times 4 plus 3 times 1. That will tell me the first entry. Well, does that check out? 2 times 4 is 8, plus 3, 11. Aha, great. What about the rest of it? To find the second row, first column, well, now I'm taking the second row times the first column. I'm going to have 1 times 4 plus -5 times 1. Does that work? Well, 4 plus a -5 is -1. Great. So I continue filling this out. We're going to have 2 times 3, right? 2 times 3. I'm looking at first row, second column now. 2 times 3 plus 3 times -2. In the first row, third column, I'm going to have 2 times 6 plus 3 times 3. In the second row, second column, I'm going to have 1 times 3 plus -5 times -2. And the last entry, this is the second row, third column. So again, just to highlight, second row, third column, I'm going to have 1 times 6 plus -5 times 3. And lo and behold, what happens? This turns out to be the exact same matrix I have down here. So using the dot product method for matrix multiplication, much quicker, right? I didn't have to write out all of this mess. And in fact, in time, as you get more practice with it, you'll start to do this dot product really quick in your head just by looking at it, and you'll start writing what each entry is as you go, right? So this is a good habit to get into. The sooner you get used to the dot product, the quicker and easier the stuff is going to be, because this method is much faster and easier to multiply than trying to use this method to multiply. Okay, great. I've shown you both methods. Let's continue. Right. So the very last piece I want to highlight here before we talk about today's participation question is one other operation we can do to a matrix. We know we can multiply matrices. We can add them. I can multiply a matrix by a scalar, so on and so forth. But what else can I do to a matrix? Well, okay, there's actually quite a few things we can do. Some of those things we're going to learn about later in chapter 2, such as inverses. That's coming. We're not there yet. What else can we do to a matrix? Well, we can take its transpose. Now, a transpose is kind of a weird idea. Like, why do we care about the transpose? The transpose is going to be very relevant and helpful for later theorems, which we'll talk about more in detail later in chapter 2. But I want to go ahead and introduce the transpose so we'll be familiar with it before we use it in theorems later. Okay, so what is the transpose? The transpose says, so definition, given an M by N matrix, if M and N happen to be equal, right? So what is the transpose? The transpose of A is an N by M matrix. Notice, what did I do here? My dimensions flipped. If A was originally a 2 by 3, well, its transpose will be a 3 by 2, right? I'm flipping the M and N here. So the transpose is an N by M matrix denoted. We'll use this notation where we have A raised to a capital T power. This will mean A transpose, where A transpose is formed by making each row into a column, or vice versa. You could also think of it as vice versa. This is also the same thing as making each column a row. So rows become columns, columns become rows. What does that mean? That seems kind of weird. Well, let's say A is this matrix, -5, 2, 1, -3, 0, 4. So this is currently a 3 by 2. So according to this definition, A transpose should be a 2 by 3. Okay, well, how does that work? Well, first, let's just look at what this says. A transpose is formed by making each row 1 of the matrix A. Row 1 of matrix A is -5, 2. That's row 1. Okay, make that into a column. -5, 2. Great. What's the second row? 1, -3. All right, turn that into a column. What's the third row? 0, 4. Okay, turn that into a column. 0, 4. And lo and behold, you just found your transpose. And honestly, it's not that much work. It's just a little bit kind of weird to get used to the idea. And then you'll start doing it very quickly. To see that the vice versa also works, it's the same thing. Make each column a row. Okay, well, what's column 1 of matrix A? -5, 1, 0. Okay, turn that into a row. -5, 1, 0. Good. What's the second column of matrix A? 2, -3, 4. Good. Turn that into a row. 2, -3, 4, right? So in other words, how do you find the transpose? Your columns become rows and your rows become columns, right? That's what's happening here. All right, great. That gives us enough that we can go ahead and look at today's participation question. So we are looking at participation day 8. And actually, I'm just going to go ahead and write this on the board just to make it a little bit quicker for us. All right. So the question states, given the below matrices, determine the result of A transpose plus B if possible. Why does the question say if possible? Well, you could see a problem in the textbook or on a What if you give two matrices that they have different dimensions? Remember, the only way to add. So is it going to be okay? Well, A is originally in the problem. Let's see. I'm going to share my screen. Share my screen. Here we go. Okay. Hold on. Am I sharing correctly? Share window. Here we go. Okay. Sharing my screen. Oh, here we go. A is a 2 by 3 matrix, right? We can see that by looking at it. So A transpose will be a 3 by 2. Well, what's B? B is also a 3 by 2. So great. They will match, meaning the answer is possible. We can figure this out. Okay, fantastic. So next we're going to need A transpose plus B. So what's A transpose? I'm going to write this on the board. So let me stop sharing the screen. And I'm quite literally just going to go ahead and write, what is A transpose? A transpose, I'm going to swap the rows and columns. Columns become rows, rows become columns. So column 1 of A becomes a row. Column 2 becomes a row. And column 3 becomes a row, right? Notice this is also the same thing as saying, let row 1 become a column. Let row 2 become a column, right? Same thing. Now, I want to take this matrix and I want to add B to it. What's B? 1, 0, -2, 3, 0, 5. Great. So now how do I add this? I'm just going to compare the entries and add them together. 1 plus 1 is 2. 0 plus 0 is 0. 1 minus 2, -1. -2 plus 3 is 1. 2 plus 0 is 2. And 3 plus 5 is 8. This will give us our resulting matrix. And so this is the final answer for today's participation question. Okay, great. How can you type this in though? Because we don't really have a way or an easy way of typing in matrices. So how do we handle this? For that, I'm again going to share my screen. So in Canvas, I want to type in my answer. Now I realize there's not like a nice and handy dandy button for matrices. Instead, I'm just going to use brackets, and I know this doesn't quite look right. That's okay. We're going to make it work. I'm going to use brackets and just type in each row at a time. So I have 2, 0. That's the first row. I'm going to hit enter. So now it's like I'm typing in a second row, -1, 1. Again, I'm going to hit enter as if I'm typing in a new row. And I'll have 2, 8. Again, okay, does this look very pretty? No, this doesn't look right. These brackets should be like a constant bar instead of like this. I realize it's not great. I apologize for that. It's limitations of Canvas. Their equation editor in Canvas does not have a matrix option. So we'll just make the most of it. This is what I'm kind of looking for today's answer, just to see that you understand how to take the transpose and how to add the matrices together. So this is what you want. Go ahead and hit submit. And that's it for today's participation question. All right. So that covers everything for today. This was lesson 8, matrix operations. Homework 2 has also been posted on Canvas, so feel free to go ahead and get started on that. There's 2 questions from each section. So there's 2 questions that went with Wednesday's lecture, 2 questions to go with today's lecture, 2 questions with tomorrow, 2 questions with Monday, and 2 questions for Tuesday. That adds up to 10, or it should. I believe it's 10 questions. So there's 2 questions that go along with each lecture, which means if you do those 2 questions right after the class, right after watching the video, that's only 2 questions you have to do. That's not a lot. And then that way, by the time Tuesday rolls around, you already have most of the homework done. And then it's not a big stressor to try to rush and get it done all in one night, right? So by all means, I do suggest go ahead and get a head start on homework 2. That will be due this coming Tuesday by midnight. Now, if you've looked ahead at the schedule, you'll also see that we have our midterm coming up. The midterm is on, it's a week from today, July 20th. And you'll also see July 19th. I don't have any lecture material listed there. Instead, in Canvas on the schedule, it says midterm review. So what that means is for July 19th, I'm going to create a Zoom meeting where we as a class can meet together and review for the midterm. Is attendance for that review session required? No. If you think you've got it, by all means, great. You don't have to come to that review session, right? Because I realize many of you have jobs or internships or maybe out of the country, this review session I'll probably do at the evening, probably the same time as the office hours. So it'll be 6 p.m. to 7 p.m. on Wednesday. Now, if you are not able to attend, I understand. So with that being said, the review session will also be recorded in case your session. All we're going to do is just kind of practice, go over things that could be on the midterm. They're going to be questions that are very similar to the homework questions, though. So if you feel like you understand everything on the homework, you're also going to understand everything on the midterm. With that being said, I also have some old like suggested exercises that students have used for additional review. So I will publish those suggested exercises for additional practice probably by this weekend. So you'll have that for next week to have that extra practice just for extra study if you want it. Otherwise, that's all for this video. If you have questions, let me know, email me, we can talk about it. Otherwise, that's all for today. Best of luck, and I will see you next class.